Okay, welcome back. We're going to continue this example. What we did so far is we took the derivative of the function, set the derivative to 0, and solved for x. We then took those x values, which are called critical numbers, and put them down on a number line. Between each of the intervals, so we have three intervals here. We have an interval from minus infinity to minus 2, an interval from minus 2 to 4, and a last interval from 4 to infinity. Inside to each of those intervals, we choose at our complete discretion any test value that we want that's inside that region. So for the region between minus infinity and minus 2, I chose -7. For the region between -2 and 4, I chose 3. For the region between 4 and infinity, I chose 11. And what we do with each of those numbers is we plug them into the first derivative. We want to know, is the first derivative positive or negative? If it's positive, it means that the function is increasing in that entire region. If it's negative, it means the function is decreasing in that entire region. I plugged -7 into the first derivative and found a positive number came out. I didn't even multiply the pieces out. I just checked, is it positive or is it negative? Multiplying them out, you can go ahead and do that if you want. It's just a waste of time. We care about it being a plus sign or a minus sign. Next is, we're going to plug in the next test value. Oh, I'll get my marker color correct. I'm going to plug the next test value into the derivative, so that's 3. So I'll have 3 times 3 minus 4 times 3 plus 2. So that's going to be 3 times -1 times 5, which is negative. That means it's decreasing on the interval from -2 to 4. So as soon as we know all the locations where the derivative can be 0, checking the sign of the derivative in between each of those x values is all we need to do. It tells us the truth about the entire region. I'm going to draw the arrow going down. And the last test value, f prime of 11. So we'll have 3 times 11 minus 4 times 11 plus 2. And that's going to be 3 times 7 times 13, which is positive, which means increasing on the interval from 4 to infinity. And that covers the entire graph. So those are all the regions of increasing and all the regions of decreasing. Let's do another one. Find the critical numbers and the intervals where the function is increasing and decreasing. So we'll start the same way. I'm not going to label the steps this time. I'm going to follow the same recipe without the numbering. So f prime of x is just 2. 0 is equal to 2. Never. That means there's no critical numbers. Okay, so no critical numbers. Now what do we do? I draw my number line. We're going from minus infinity to infinity. That's our domain because it's a polynomial. And we have nowhere to cut the number line, so I'm going to choose a test value. I'm going to choose a test value of 15. And then I'm going to plug it into the derivative. So f prime of x is equal to 2. F prime of 15 is equal to 2. Like f prime of x is always 2 for all values of x. It's a horizontal line. So f prime of 15 is equal to 2, which is positive, which means f of x is increasing on the interval from minus infinity to infinity. So we used the recipe, even though we didn't really need the recipe, knowing this is a straight line with a positive slope. But we use the recipe anyway to confirm that it recovers the same outcome as just knowing what the function looks like visually or graphically. And it's not decreasing anywhere, it's only increasing. All right, Next one, very interesting question. Determine the critical numbers in open intervals where the function is increasing and where it is decreasing. Oh, and I gotta go back and fix something. No, I don't. I don't have to fix it. I just have to make mention of it. A critical number must be in the domain. That means you must be able to plug it into the original function. So watch that here. Okay, so first step is to take the derivative, but actually step 0 is going to be to get the function ready for a derivative. You can set this up as a quotient rule if you're desperate, but it's easier to do this, to rewrite 1 over x as x to the power of -1, then take the derivative. So 1 minus x to the power of -2. Now I'm going to set the derivative equal to 0. 1 minus 1 over x squared is equal to 0. I'm going to add 1 over x squared to both sides. So 1 over x squared is equal to 1. Then cross multiply both sides by x squared. So 1 is equal to x squared. And that means we're going to have two solutions. We're looking for all the x values that will make this true. We have x is equal to 1 and x is equal to -1. However, we have another value to worry about. And f prime of x does not exist dne at x equals 0. It causes a division by 0. So all of that has to go on our number line. Okay, so that's the next step. So we're going to make our number line. Our number line goes from -infinity to infinity. We have a problem at 0, but we're going to label it. So we're going from -1, 0, 1. And we have to choose a test value in each of these 4 regions. So a test value from -infinity to -1. Let's go with -5. A test value from -1 to 0, well, decimal or fraction. We have to pick one. I'm going to pick a fraction. I'm going to pick -1/2. You can pick -0.5 if you want. It's the same thing. You can also do -1/3 or -4/7. Okay, and I'm going to pick +1/2 on this side, and on the right-hand side, I'm going to go with 3. And those are our test values. And they're just arbitrary. I picked them. If this was a class, I would wait until someone else picked them. I wouldn't pick them myself and make you pick them, but you're not here, so I have to do it. Next, we plug each of them into the derivative. f prime of -5 equals 1 minus 1 over -5 squared. So I'm using this line, the third line for the derivative. The f prime of x is 1 minus 1 over x squared. So I get 1 minus 1 over 25, which is 25 over 25 minus 1 over 25, so 24 over 25. What matters is that this is positive. So it's increasing inside that region. So increasing on the interval from -infinity to -1. Now I'm going to check the next test value. I'll choose a different color so it's easier to identify which one's which. F prime at -1/2. So we have 1 minus 1 divided by -1/2 squared. So that's 1 minus 1 divided by 1 over 4, which is 1 subtract 4, which is -3. So that means f of x is decreasing in the next region. Decreasing on the interval from -1 to 0. I'm going to check the next region. I'm going to pick another test value. Positive 1/2. So 1 minus positive 1/2, 1 over positive 1/2 squared. So 1 minus 1 over 4, 1 minus 4, which is negative again. So it's decreasing this region as well. On the interval from 0 to 1. And then we got one more. We have our last test value. F prime of x, or f prime at 3. That's 1 minus 1 over 3 squared. 1 minus 1 over 9, which is 9 over 9 minus 1 over 9, so 8 over 9, which is positive. So f of x is decreasing on the interval from 1 to infinity. And, oh, sorry, increasing. What am I saying? It's increasing. It's positive. So an up arrow for the last region there. Now what does this graph look like? X plus 1 over x. We have this weird thing happening at 0. There's a vertical asymptote, this infinite discontinuity. And we have a spot where it's going up and down, and it's going down and up. Looks like this. So notice our picture with our arrows, up, down, and then down and then up, down and up. It's kind of like a very rough sketch of the graph. And we're gonna do a lot better than this when it comes to sketching graphs using calculus or sketching graphs using derivatives. But this is kind of a starting point, that it's a very basic sketch of the function. Those arrow diagrams. So regions of increasing, regions of decreasing labeled. And let's continue in the next video.